Good morning, my name is Ignacio Hidalgo, and I'm going to present you the work title Profile Glucose Forecasting using Genetic Programming and Clustering. This work has been developed at the Universidad Complutense de Madrid in Spain and is a part of the work of the PhD thesis of Sergio Contador, which is also directed by Oscar Garnica and Manuel Velasco. This work is about predicting glucose values for helping diabetic patients. During my presentation, I will follow the outline you can see here. First, I will give an introduction explaining the objectives of the work and in particular some notes about what is the diabetes. Then I will explain the methodology followed in this work, and I will explain the different part of it. In particular, I will give some ideas about the data collection, the pre-processing and division of the data. Then the data clustering we perform to improve the training, the quality of the models we obtain by evolutionary computation. And then also how we select the best model using the KK criterion. I will give also, of course, some experimental results, and I conclude the presentation with the conclusions and the future work. So, what is diabetes mellitus? Simply diabetes. Diabetes is a group of disease that is characterized by a high level of blood glucose levels, and resulting from either a defect in the production of the insulin or a defect in the action on the insulin. And so we have the two main class types of diabetes: the type 1 diabetes, which is usually appears in the earliest age of the people, in the 18s and in the teens ages of the people, and then the type 2 one, which is usually a problem of resistance to insulin, and started usually after 50s. It's a problem of the society. It's an economic problem also, because all around the world, more than 400 million people are suffering this disease. So the diabetic patients need to control the glucose levels in order to avoid not only short-term complication but also long-term complication. The objective is to maintain healthy levels, what we call normoglycemia. This is a concept that I will explain in the next slide. And the patient should avoid the high levels during a lot of time, because high levels of glycemia in the blood makes the organs suffer a lot of complications, like retinopathy, like cardiac heart problems, like and other things. And the low levels are also necessary to avoid, because at short term, when the patient go very low levels, this can produce a diabetic coma and even the death of the patient. So for this, now it's extend the concept of time in range. So the objective is to maintain the patient in time in the higher time in range. The higher the time in range, the better the control. And the time in range is defined as the percentage of the time that the patient spend with values on values uh, among 70 and 180 milligrams per deciliter, which is the usual way of measure the glucose. So the objective is to avoid those peaks that you can see in the center of the figure, and to try to increase the green part of this diagram. So when the diabetic need in order to control the blood, when the diabetic is going to eat, he or she needs to put some amount of insulin, and the amount of insulin needs to be the proper one in order to maintain the glucose in range. So the goal is to create a methodology to obtain a accurate prediction in order to help the diabetic to know what is the level of glucose he or she is going to have in the next future in order to maintain this. And so the patient can adapt the amount of insulin he or she is going to inject. So we want to obtain a method to obtain model based on the data recorded by the patient. In particular, we'll use glucose level measured by a continuous glucose monitoring system or a flash monitoring system, like in the figure. The down figure is a freestyle libre of Abbott. Also knowing the amount of carbohydrates he's going to eat or she's going to eat, and also the information in the past, and of course the information about the insulin. The insulin as usually put with a insulin pump, like in the figure we have the Medtronic one of the Medtronic. So the methodology we will follow in this work is, first, of course, we make a collection of the data using several devices, in particular those I mentioned in this in the previous slide, and also some notes of the patient about the carbohydrates. And with this data, we create a database where we can perform the pre-processing of the data, filling the gaps, eliminating outliers, and so on. Usually typical operations in data science. And with that, we divide the data in this world in several parts. In particular, we make a division in 4 hours files. That is, we would have the data, for example, for 15 days, and we take each day and divide each day in 6 parts of 4 hours. And with this, we have all of this separated and tagged, and we perform a clustering in this world using a child algorithm, but we can also use other methods. And then with this, we obtain different clusters that we will use to train different models. Sometimes we also need to make a data augmentation because we have a low cluster with a low number of datasets. With this, we train models, as I told you, for each cluster. Then, which is on each cluster, we also select the best model and assemble the model finally for obtaining a predictor. And once we have performed all these steps, we can start to make prediction to help the patient. So the The first part, as I told you, is just to collect the data. In this figure, we can see the data from the continuous glucose monitor system. Like we can also include the insulin pump, and we divide the data by this division criterion. In this word, as I told you, the day and the time slot in the day. But we are also working on dividing the data by foods, that is breakfast, dinner, and lunch, and also different parts. So then we perform the data clustering. As I told you, we are using chi-square automatic iteration detection, which is a clustering technique, popular clustering technique, but we can use any other clustering. For example, in this figure, we can see k-means clustering, where also perform quite good. We select first this shade clustering techniques because it's based on decision trees, and we don't need to identify previously the number of clusters we need in k-means. And the objective finally is to discover glucose profiles that identify similar situations in those patients and incorporate this knowledge to the model, in this case by making different models for each cluster. So we classify these glucose values into groups. Here is the division we use, and then nomenclature we will see in the slides. So each group identify a time slot starting from noon, and then we also may put a tag on each cluster depending on the day of the week we are dealing with. And then we perform the model training with one of these clusters, and we process using genetic programming. In this particular case, we use the heuristic lab software from University of Applied Science of Upper Austria in Linz, Austria, and we make a cross-validation, obtain the ensembler model and the predictor. And for obtaining the models that are going to participate in the ensembler model, we select the best ones using the KK information criteria, which is basically we select, if we have two models with similar qualities, we will select the simplest one. And this is made by this formula, which is explained in the paper. And in order to measure the quality of the solution, we are going to use Park's error grid, which is a grid that was designed to assess the clinical accuracy of continuous blood glucose monitoring systems. And the idea is to have a normal grid of prediction, as usually you can see, but we divide the grid in different zones depending on the dangerous of the misprediction. For example, depending on the quality, on the danger. So A and B are zones that are safe, but then C, D, and E are progressively more dangerous. Well, for example, if we have a prediction on zone E, that means that we trust this prediction, we are going to have a decision in the treatment of the patient that is different from the one that the patient needs. So we are going to make a misprediction that is dangerous because we are going to recommend somehow the patient to do a dangerous thing. For instance, if we can see in the graph, we are representing the prediction versus the actual value. So, for example, if we have in this graph a point here in the 400 value of the glucose, that is a prediction in this point, but the real value is a value in this point. That means the representation is here. So we are in zone E because this corresponds to a hyperglycemia. The prediction corresponds to a hyperglycemia. So the patient, what should do is to put more insulin, but in reality, the actual value is a low value. So if the patient put this insulin, is going to die. So this is the point. So the objective of our algorithm is to reduce the number of prediction, especially in zones D and E. And we can say that we obtain prediction with very high values on this zone, practically with very just punctual one. And here we can see first the groups obtaining with the clustering algorithm. So we reach to classification on different groups. So we obtain different profiles for the patient that then we use to make the prediction. Here we can see, for example, for 5 different patients, and we obtain similar behaviors. For example, for the patients during the nights, which correspond to time slots 0 and 1, and for Mondays, Wednesdays, Saturday, and Sundays. So during the nights, we can see that the behavior is very similar. So we can make a model for this for the nights of this patient. And also, for example, this patient during the Fridays usually has 2 behaviors, one that corresponds from 10 of 0 and 5, and the rest of the day, which probably means that this patient goes to bed later and usually have more time, spend more time sleeping during the Fridays or something like that. So here the first result is that, of course, using a clustering algorithm, we can identify those profiles, which can also be helpful for the medical doctor, the physician, to adapt the treatment of the patient just looking at these colors. And if we use this model to train the genetic programming, or to use genetic programming to train models with this division instead of using all the values for one patient, what we see here in this slide is the ratio of the model with better prediction, that is with higher values in zones A and B, when we use the clustering algorithm. As we can see, the prediction using the child GP are better than using the GP for the different patients, and in this case for the different time slot, time windows, sorry. And also here we can see for different time windows, the prediction are also better in most of the cases. And going to the numbers, which is more interesting also since we are looking for the prediction in zones A and B, we can see that, of course, we also obtain only with GP good prediction, but in most of the cases, we improve the prediction. Here we are seeing again for 5 patients, the values are also similar for the rest, but we can see here the prediction using GP and Chase GP. And we see that in green that most of the cases the predictions are better for different time horizon. Here we are seeing for 30, 60, and so on time horizon of prediction. So we can conclude that first, significant differences are found, an association on different clustering and are observed between the glucose profiles classified using the independent variable only the day of the week and the time slot, which is a very simple decision. And then the accuracy of the prediction with model created with genetic programming is better than for shorter time horizons, and gradually gets worse as the time horizon increases from 30 to 240 minutes, that is 2 hours. 4 hours, sorry. In general, when using classified glucose values in models created with traditional GP, the accuracy of the prediction of the glucose values improves in comparison with those of models created with the original dataset. And significant differences found in the classification can be also useful for correctly improve the habits and therapies of the patients, and the results will facilitate also the mathematical modeling of glucose in future works. So in future work, we will divide the glucose we are working on, glucose time series into different meals. We will use also the other approaches in genetic programming, and we also complete the general method with different techniques using grammatical evolution previously. Finally, I want to thank all the institutions that help us financing this work. First, the Fundación Eugenio Rodríguez Pascual, which is a foundation in Spain, and also the government of Spain with the national projects, and also the European Union through the Community of Madrid, the Madrid government, regional government, with 2 projects, the Genovia project and the microstress project. So this is all. Thank you for your attention.